There we go. All right, so I did want to do a quick wrap up of 2.6. So we talked about best fit line in 2.6. And I just wanted to show, well, you, Connor, and then anybody that's listening, how you actually do the best fit line on Desmos and have it kind of recorded so that you're able to see this. So if we go back to, well, I don't know, we could just make up some data. Let's see. I'm not very good at making up data. I don't have my book with me. Just got to find some data really fast here. I guess I'll use the data that's on our homework sheet. So I know we did this in class, but so if you want to enter data into a table in Desmos, you're going to go, and I kind of did it without even doing it. You're going to go to the plus button, and there is a table feature. So that lets you put a table, and actually you can have more than one table. But we just need one today. So you're just going to enter the data in. So we have 12. This is just the data that we used on Fridays or Monday. It's not super exciting, but what did we decide? It was the your age and the number of presents you get or something like that. Okay, 75. Always more fun when you come up with something like that. Okay, so we have a table of data, and then if we want to use Desmos to make the best fit line for us, it's kind of a weird syntax the way you do it. So what you're trying to do, the line that you want it to model is y equals mx plus b, right? Because that's a line, and that's what we want to model it after. But you can't, unfortunately, just type in y equals mx plus b. And I'm a little distracted here. I'm going to move my graph so that it actually shows what I have. So 1 through 70 for my x's and 0 through 110 for my y's. There we go. So you can actually graph the data. It just wasn't showing before because I was not in the right graph settings. So if you want to change your x and your y axis, you just go up to this graph settings and you're able to do that. All right, so we are trying to fit this set of data, which is plotted out here, into a line. So you can see I typed it in and it doesn't really, too many variables, try defining M or B. So what we're actually trying to do is we're trying to figure out the data, and you can see they've labeled it for you, is in a table with the x's are x sub 1 and the y's are y sub 1. So we actually need to represent that in our equation. So we're actually going to use y, and then this is, when if you go under the alphabet, there's this a with a sub. So y sub 1. Oops, I would erase my data. I've never had to do that before. X, oh, there it is, x sub 1. Okay, but now it's mad at me. It says this column header can't be defined, So it's kind of mad at me when I type it in like this, but that's because I have an equal sign in here. So when you do a best fit line, you're approximating something. And so the way Desmos kind of defines that is by this little squiggly line. So you can see all of a sudden, once you put the squiggly in instead of the equal sign, you're telling it to approximate the line that best fits this data. And so you'll see that it tells you that your slope should be negative 1.78. Your y-intercept is 119 up here, and that your R value is negative 0.995. So we talked on Monday that the best R value we can get is 1 or negative 1, and we came really, really close. So this data can be fit really closely. So this will actually give you the best fit line for a piece of data, data that you have. Now let's put in something. I didn't do this on Monday, but if we put in like an outlier, so an outlier is a piece of data that doesn't really fit. So we know here it has 50 is 26. What if I put in for 52, we have a data point at 70. Okay, so I have this additional data point that I just entered in, and you can see that it kind of shifted my best fit line because it's trying to include that the best that it can, shifted it a little bit, and now my R value went down right? It went down to negative 0.85. So it's still a pretty good best fit line, but because we have this outlier here. Hey, Sarah, how are you? That kind of shifted it. So now if I enter in more data points that are kind of close, so I had 25 and 75. If I put it for 23, it's only 30. You can see we're starting to kind of get worse and worse with our best fit line, right? We really can't fit our data as well as we can. Sarah, I'm just using that data that we had, our presence per age, or presence, age, and the number of presents. And I was just kind of showing in Desmos again how you can use a best fit line. And then what happens if we enter some new data, these points here, that really aren't on our line, how our R value just goes down and it just becomes worse and worse. Cool. So Sarah, if you have your calculator, I think we did this on Monday. We kind of figured it out at the end. I wish I had an online. I wonder if there's an online thing. I should look. You're actually going to go under the stat button, STAT, which is top middle. Let's see if I can do this on here. Give me 1 second. Let's see. I'm just Google searching for, I paused the screen. I'm Google searching for no, that's not it. No, I wish I could like put it up on here, but yeah, Sarah, you're going to go under the stat button and you're going to edit, and then you'll have list 1 and 2. And then you're going to go, once you put your list in, you're going to go back and you're going to calculate, which is also under stat, the linear regular, so number 4. All right, yeah, you try that out. Sarah's going to try that out. So that's how we do best fit lines. I don't have a nice calculator. Oh, whoa. This does not look like a calculator, but somebody made some crazy thing out of Desmos that looks like a calculator. I'm like, oh, does it actually work? That would be pretty cool if it did. I think somebody really took the time to like figure out how to write the word log using all kinds of crazy things. All right, that's interesting. Not helpful to what we're doing, but interesting. So I think that's a good wrap up of best fit line and kind of how that works. If we put some really, really crazy data in there, let's say 27 and like negative 100. Zoom out here. So we put this data point down there. All of a sudden our R value, which remember is the correlation coefficient, is not very good anymore. Wah, wah, wah. But if we go back to our original data set, we get a very nice best fit line that represents all our data. Okay, so that is that. Sarah, let me know if you have any questions about your putting your list in. The other section I wanted to go over today is 2.7, use absolute value functions and transformations. All right, so absolute value, who remembers absolute value? Did we talk about absolute value yet? Okay, we did talk about absolute value. All right, cool. I thought I have in my notes, we've learned about it, but now we're going to look at their graphs, but I just want to make sure. So absolute value function just basically means that you're looking how far your value is from 0 on a number line. That's right, we did talk about it, Connor and Sarah. So let's talk about what a basic absolute value function looks like on a graph. So again, let's pull over to Desmos here. Get rid of this. So y equals, minus y equals, and then we're going to do absolute value of x. There's actually a function for this. Okay, enter. And I'm going to go ahead and set my range back to square range. There we go. On your TI calculator, there is an absolute value function, and it is, Sarah, if you hit math, the math button, and then number. So the first thing is ABS. Okay, yeah, so you can actually graph this on your calculator. You would just go into y equals, and then you would put this ABS x. All right, so let's look at the graph. It's kind of interesting, right? Absolute value function is kind of interesting. And it makes sense, right? If you put in x equals 1, you get, oh, I'm on a different scale. If I put in x equals 1, I get y equals 1, right? Because 1 is 1 unit away from 0, and that gives me my absolute value. If I put in x equals -2, my output y is +2 because -2 is 2 units away from 0 on the number line, right? So I get my +2. So absolute value functions are kind of interesting because you kind of get this sharp turn graph, which you don't get a lot in math. A lot of the graphs that we look at are going to actually be polynomials, so they're kind of curving a little bit. But this is the standard graph of the absolute value function. So that's kind of the first thing that we want to note. And then we want to talk about actually how we can transform the graph and how doing different things to our absolute value function translates or transforms our graph. Okay, so the first thing we're going to talk about is translation. All right, so a translation of a graph actually shifts the graph either horizontally or vertically. So I think the best way to kind of play with this is that we're going to talk about some translations of the standard absolute value function. All right, so if I have another y equals, not plus, equals absolute value of x, okay, the same function. And then I add 2 to my overall function. So you can see it's not inside the absolute value, right? But I've added 2 to my absolute value function. So by adding 2, I actually am able to translate the graph and shift it up by 2 units. All right, so when you add, if my whiteboard will let me do it here. Trying to draw on here. Doesn't want to let me draw on here. Okay, so we're adding outside of the absolute value function, right? We're adding +2. And so this gives us a translation of moving the graph vertically +2. So everything just gets shifted up. The graph stays the same, but everything gets shifted up, right? What do you think is going to happen before I turn it on if I do the same graph, but instead of adding 2, I subtract 2 from my absolute value function? It's going to shift the whole graph down, right? Every point is just going to shift down by 2. And I think this makes sense. Like if you plug in a number, you know, x equals 1, 1 plus 2 is 3. So you can see that it shifts up here. You know, 1 and 3. And then you can see if you subtract that it shifts down. So that's how we can actually take the standard graph. So when you're translating, you're not changing the original graph. You're just moving it off of its original 0. Its parent function, it's kind of called. All right. We can also shift our original graph to the right or the left. So we can actually shift it horizontally to the right or the left. This one is not quite as intuitive, but it makes sense. So you'll notice when we have +2 and -2, those are outside of our absolute value. So absolute value of x is in here, and we've added 2 and we subtracted 2. Okay. what happens if we take our same graph here, chop off the +2, and now inside the absolute value, we add 3. So let me actually hide these two for a minute. So we have our original absolute value function, and then inside our absolute value function, we've actually added 3. So when you add inside the function, it's actually going to shift your graph to the left by 3. All right, so these are a little more intuitive. Plus, it's going to shift vertically 2. Minus, it's going to shift, down 2. When you're dealing with the horizontal axis shifts when you're inside the function, but it does the opposite. And then if you kind of unpeel it a little bit, it makes sense, right? If I put in, yeah, it is kind of cool, isn't it? If you put in -3 and you add 3 to it, you get 0. So the point, when you get down to the actual data, it makes sense. I think it would make more sense if you had x -3 and then it went to the left. I don't know, because you think of the left as negative. At least I do. So then, shocker, if we have x -3 inside our absolute value, then it's going to shift horizontally to the right 3 units. So kind of eventually when you get to a point, and I know that we were doing this in pre-calculus, the first few weeks of pre-calculus. So if you keep on taking calculus or any other math classes, or if you're taking your SAT or ACT, sometimes they actually might give you these problems without your calculator. Because obviously you can type this in your calculator and tell where it goes. But the idea is understanding that if you have a function and that you add outside of the function, it shifts the graph up. If you add or subtract outside the function, it shifts the graph down. If you add inside the function, it shifts the graph left. And if you subtract inside the function, it shifts the graph right. That was a bunch of words. But basically this concept that you can move around your standard graph and kind of have a feeling for that without even using your graphing tool. So the idea is that I could, give you, for example, y equals, what I'm trying to do. Desmos is so polite. I'm sorry, I don't understand what you're doing. I'm going to hide this graph. I'm not going to make a graph. So if I gave you x equals, or the absolute value of x -4 plus 5. Okay, so this graph is not turned on right now. But just based off of our knowledge of what we learned up here, could we figure out where the new version of this graph would be? All right, so we learned up here in these first two, right? When you add outside of the absolute value, you shift up by 5, or you shift up when you add outside. And then in this particular case, we're adding 5. So our new point is going to be, yes, that's right, Sarah. See, you can kind of test yourself before you do it. So I know our new point is going to be up here at +5, right? But then I have 2 translations going on because inside of my absolute value, I have -4. And again, when you think -4, you automatically kind of think negative on your graph. But because it's inside the value, you actually shift to the right. So our new absolute value function should kind of have its point down here at 4, 5. So it should kind of go there. So then what you can do is kind of test yourself. Voila. And see that this translation makes our new graph at 4, 5. I don't know. I think it's kind of cool. You can make pretty graphs with it if you put everything up at the same time, right? You get a bunch of absolute value lines. Looks like a retro design, I guess. So that's translation. So 2.7 really is all about doing some translations and seeing how that affects the graph. Okay. Now there's one other thing we didn't talk about, which is called transformation. So translation, if you notice when I have all these graphs up here, right? It's the same graph. We're just moving around basically where the bottom of the absolute value function met at 0, 0. And we're just moving around where that point is. But the graph itself is staying the same. Okay? And that's translation. With transformation, you're actually changing the graph size, shape, position, or orientation. So let me show you a couple examples of some transformations, and you can kind of see how it's different. So with translation, you're doing all with addition and subtraction. With transformation, we're basically using multiplication. So what happens if I make this y equals the negative absolute value of x? Okay, so my original absolute value function is in green, and my new absolute value function is in orange. So this actually doesn't change the exact size, but it flips quadrants, right? The negative makes it go from a positive opening up to a negative opening down. Yes, it is sneaky, isn't it? What happens if, so again, I think these are just good things if you have your calculator up just to play with, like type these in, see what happens. I'm going to turn off the graph. So what happens if I put a 2 in front of my absolute value? So what do I think is going to happen to the graph? So when I multiply by 2, I think my graph is going to, or my absolute value function is going to rise a lot faster, right? Because every value that I get out is multiplied by 2. So when I multiply by 2, again, the adding and subtracting just move the graph around. That's translation. Multiplying, by positive or negative numbers is transforming the graph, right? So then if I multiplied by, this one by 4, and I turned it on, then you're going to get an even greater absolute value function. Okay. Now, what if instead of by 4, I multiply by 1/4? So now because I'm multiplying by 1/4, I'm slowing down the graph, right? And so my graph is rising at a much slower pace. And then of course you could, I could do -1. No, 1/2, that's 1/2, 1/4. And then if I put my -1/4, it's reflecting across my x-axis. So then if you're feeling really good, what you want to do when you're in your homework is you want to take a problem like this and see if you can kind of figure out, this is kind of off your paper, -3, and we have x plus 1 minus 2. So this is combining everything together. Okay, so we are translating and transforming a graph. So let's see if we can figure out, just based off this, before I hit the, make it visible button, let's see if we can figure out where we think this graph is going to be. Okay, so the first thing, I'm going to work my way kind of outside. The whole thing is being subtracted by 2. So since the whole thing's being subtracted by 2, I know my graph is going to shift down 2 units. So I know that I've got that going on. Inside my absolute value, I'm adding 1. Okay, when I add 1 inside, that means I'm going to shift to the left 1 unit. So I know my point's going to be right here. I really wish I could draw on the screen. Okay, let me see if I can get my whiteboard to let me draw. Okay, shift down to 1. Oh yeah, it's letting me draw. Okay, so I know that this point is getting translated down here, right? But it's also being transformed by -3. So the negative means that my graph is going to flip, right? It's going to flip the other way. And it's being multiplied by 3, so it's going to go 3 times as fast It's going to basically grow 3 times as fast. So maybe something that kind of looks like this. So just kind of think in your head as you're doing these, okay, what do I think this is going to look like? All right, and then when you actually go to do your work, let's see, much prettier than what I drew, but you're able to kind of estimate, oh, okay, that's what that graph's going to look like just purely based off of looking at the numbers in the equation. So this is one of those tricky things when you have the non-calculator portions of tests, like your standardized tests. They like to ask a lot of questions about transformations and translations, because it's kind of like feeling how the graph changes. And then the cool thing about this, well, you know, cool in terms of Algebra 2 cool, is that this applies to any function. Okay, so remember how, let me clear everything off here. So we just applied all these concepts to absolute value function. And this is not in this particular section, but I just think since we're here, we should say this applies to any function. So we're going to talk a lot about quadratic functions, right? Y equals x squared. Well, guess what? If you do y equals x squared plus 5, right? The plus 5 is outside of your x squared. Your x squared is your original function. It's going to shift your graph up 5 units because it's outside of that. If you subtract 5, it's going to go down 5 units. Inside the function would look like y equals, x plus 2. Oh, I figured out how to do that on there. Okay, x plus 2 squared. All right, so you can see the plus 2 is inside my function, and that makes my graph shift to the left by 2. And then, so that's all the translations. And then if you talk about transformation, right? Transformation is outside of it. If I have, y equals 2x squared. No, I'll make it better. We'll make it like 10x squared. There we go. You can see that this transforms my graph and makes my parabola open up a lot more quickly. So these same principles that we just talked about for absolute value functions apply to any standard functions. There's your standard quadratic function. There's your standard absolute value function. I'm trying to think what else. I know there's a whole list of them. So the kind of the principles work across the board of how adding or subtracting in or outside of the function or multiplying changes your graph around. All right, Sarah said she likes this, so she's going to try to draw something. You should, Sarah, if you go online and look up Desmos like artwork, there's some really fancy art that people have done using Desmos calculator, because you can come up with some really cool things. Yes. So that's all I wanted to do today. I think it helps to, well, this section obviously just lends itself to being online and being able to see on the calculator. So that's what we are going to do today. So thank you both for coming. If you have any questions, you can hang on. If not, have a great day, and I'll see you on Monday.